Hi everyone and welcome to this video on the reciprocal circular functions, part of the specialist maths course here in Australia. Don't worry if you're not in Australia or in fact doing specialist maths, this course is universal and basically it will teach you all you need to know about the reciprocal circular functions. At least I hope it will. My name's Darren from Maths Guru. Thank you very much for watching and let's get going. Behind me are our learning objectives. Understand what the cosecant function is and what it looks like, secant and cotangent functions looking like. Understand the useful properties of each of the above and understand how to use the cas to solve functions containing the above. Okay, that sounds like a big order, yeah? Right, well, let's recap some of the work that has gone before in this particular course. Now, we already met the idea that we can use the sec and tan functions with parametric equations to help us form from parametric to Cartesian form. And if you haven't got any clue what I'm talking about, that's fine, the video is coming if it's not already there. Knowing what the shapes of graphs are is critically important. In fact, that seems to be the whole of the methods course. If you remember from methods, all you seem to do is sketch curves. And to be able to do that, you've got to find things like x-axis intercepts, y-axis intercepts, maximums and minimums. Now, whereas some people out there, I am sure, just memorize these things, wouldn't it be great if there was a sort of hard and fast way of sort of working it out if you actually needed to? And that's pretty much what I'm going to do with this video here. So let's start with the graphs of sine theta and cosec theta. Now, obviously, sine and cosec are reciprocals of each other. And the way I tend to teach this is I say, well, okay, I always start from the base function. I know what a sine curve looks like. So if I draw a very quick sine curve, there we go. So we know that's 0, we know that's pi, and we know that's 2 pi, have a maximum of 1 and a minimum of -1. Everyone knows that. Everyone should be able to start with that. But what would happen if I reciprocated that? Now, what I tend to say is this. Well, if I do 1 over a really small number, what's that going to be? Well, hopefully the answer to that is it's going to be a big number. And if I do 1 over a big number, what's that going to be? It's going to be a really, really small number. And obviously, there goes without saying in this situation that there is one value that sine theta cannot be, and that's 0. So before I even go any further, I know that these crossing points here are going to be special in terms of my cosec graph. Why? Well, because sine theta can't be 0. Ah, okay, well, if it can't be 0 and these points are 0, it suggests that ultimately whatever graph we're going to draw is going to have asymptotes through 0, pi, 2 pi, 3 pi, 4 pi, and so we go on. Now again, we know there are certain points on this graph that are actually really, really important. And so if I look at this point here, I know that that maximum has a value of 1. So my cosec graph would have a maximum of, no, not a maximum, sorry, a minimum of 1 as well. Why? Well, because at this point here, which is pi on 2, we know that that value there of sine theta is 1. So 1 over sine theta is going to be 1 on 1. So I now know there's going to be a point there on my cosec curve. Likewise, if that's -1, 1 on -1 is -1, we know there's a point there. And the way I tend to describe it now is, let's go all the way to the end, that little point there that I'm highlighting on the sine curve, yeah? So for that really small value of x, or theta, sorry, what am I going to have? Well, that really small value, 1 over that really small value is going to give me a really, really big value. So imagining that we got a point all the way up here, somewhere. Likewise, this point here is going to be somewhere up here. This point here, my values are getting bigger and bigger and bigger. And if you remember, 1 over a big value becomes a much smaller value. And what you tend to find is that your graph is going to look a lot like that. Oh, pretty. Right, so bearing in mind that's going to be an asymptote, that's going to join there, and it's going to shoot back up again. What about here? It's going to go really big negative to there, right? And again, that's really the way I tend to do this in my head. Why? Because it just makes sense to do it that way. If I can start from first principles and all else fails, then at least I can work something out in the heat of an exam. Right, so let's now look at, the important information. We can now see for cosec that there are going to be asymptotes at n pi. Now, again, why? Because it's 0 pi, 1 pi, 2 pi, 3 pi. That's where the sine curve would cross, yeah? We know the domain for cosec is going to be all real values. Again, it's going to be all real values except n pi, which is where my asymptotes are going to be. The turning points are going to be exactly the same as they were for sine theta, because there's a turning point there, there's a turning point there, and as we keep going, whatever else. And again, it's really important to know that the range of a cosec curve is going to be all real values except -1 to 1, not inclusive. And again, if you remember, my range is going to go all the way down to that 1 value and go back up again. It is never going to have any of these values here that the sine curve actually populates. All right. Now, again, if all else fails, you have your calculator to try and help you work this out. But that, to me, is how I normally teach the graphs of sine and cosec. Now, what about the graphs of cos and sec? Again, sec is the reciprocal of cos. All right, so, and you got to be very careful here not to get confused with the idea of reciprocal and inverse. All right, the notation will confuse people left, right, and center in specialist maths. But again, sec theta is 1 on cos. Well, again, if I draw a quick set of axes here, and we'll just deal with one revolution of cos. There we go. So what do we know? That's 0, that's pi on 2, that's pi, 3 pi on 2, and 2 pi has a max of 1 and a min of -1. Now again, if we look, important points suggest that changing color, that there and that there is going to present some sort of a problem. Why? Because of that points there, for those values of theta, cos theta is 0, and we know that actually cos theta can't be 0 here. All right, because ultimately it's going to create an asymptote. So drawing now, I've got some asymptotes there at pi on 2 and 3 pi on 2. So we've got some asymptotes at pi on 2, 3 pi on 2. Where else would they go? Well, we'd add on 2 pi to every one of those. But again, what we're now going to start to notice is that the coefficients are going to be odd numbers, right? So we can get that in just a moment using the information we've had from methods or previous parts of the course. All right, so let's have a look at this now. What else do we notice? Well, like the sine curve, we're going to have the same turning points because that point there is 1. 1 on -1 is going to give me a point there. That's -1. 1 on -1 is going to give me a point there. And again, if we use my highlighter, that's a really small value of cosine theta. So that's going to have a point up here. And again, if we think of the same idea, it's going to come down like that. And it's going to go up and down like that. And again, it's going to go down like this. And realistically speaking, again, if all else gets confused, that's exactly how I tend to do this in an exam. All right. And there we go. So that, again, is my basic idea of what my sec graph would look like. Now, again, how do we find out where my asymptotes are going to be? Well, here we go. Now, sorry for it being so small, but 2n plus 1. Again, if you remember, to be able to get my even numbers, all right, it's 2n, where n is in integers, yeah, or 2n plus 1 for n is in integers again, if I want to find my odd number. So that explains where the 2n plus 1 comes from, and the pi on 2, again, because that's where my cosine curve would normally cross. What is my domain going to be? Well, basically, it's going to be all real values. We know that cosine is all real values, but now we've got to be careful here because it's going to be all real values except wherever I have these asymptotes. So there's my domain. And what about my range? Well, exactly the same as the sine curve. Why? Because we realize that when we draw this graph, there are no values for that between 1 and -1. All right. So again, this all helps to build up in my head. If I understand where this stuff comes from, then I don't really feel like I'm regurgitating, and I should be able to have an idea of how to use this. The tan graph and the cot graph, and again, cot is the reciprocal of tan. We are going to look for the idea here. And again, this is really a bit of a stretch of the imagination. And by this point, I'm normally saying to people, look, just accept this one because in my head, it's not as easy to show as otherwise. But what we can find is, here is my graph, or here is my tan graph, all right? And what do we know about my asymptotes? They're going to be pi, so that would be negative pi, pi, 2 pi, and so on. So again, we'd have to be very careful here that these points on my cosec graph, cotangent graph, are not going to exist. They're going to be asymptotes. So again, if we look here at pi on 2, so there we go. So that's going to be an asymptote. I'm looking at the red graph, by the way. There's too many graphs on here to look at. Yes, so they are going to be my asymptotes there. And what we find is that the cotangent graph is effectively the tan graph with a translation of pi on 2 to the left with a reflection in the x-axis. Just take that as fact, right? The domain is basically, again, real, but excluding our asymptotes, which will be n pi. The range is real, all right? What we notice is there's no values for my cotangent graph that don't exist from sort of infinity to negative infinity. And again, my asymptotes can be found at n pi. All right, so that's the looks of the graphs. And if we were asked in an exam to sketch the graph over the interval 0 and 2 pi of y equals cosec of 2x, the first thing I'd be saying to myself is, well, okay, cosec is the inverse of what graph? Sec, you muppet, sine. So again, I'd be looking at this going, well, my standard sine curve would look like this, which would be 0, pi, and 2 pi. Obviously, we have some sort of a dilation. We have a dilation towards the x-axis, from the y-axis of factor a half. So that means that that is going to be pi on 2, and that's going to be pi. Yep, okay. So what do we notice here? Well, if I now wanted to draw that, because these are important points, highlight these important points, because these points here I think are important, that is now where we're going to have some asymptotes. So there's going to be an asymptote there, an asymptote there, an asymptote there. Now again, because I've got to be careful, right, at the moment, this now has a domain between 0 and pi. My original question said between 0 and 2 pi, which I now know means I'm going to fit 2 of these periods into. And again, knowing that I've got the idea now that that's going to do this, and it's going to do this, and it's going to do, this, then obviously I can now draw this as accurately as I can, because I've got all the information that, once I've got the idea that we've got my crossing points here, or my asymptotes there, then the rest of it's really just drawing these sections in, making sure that they go to 1 and -1 and whatever else. And again, here we go, pretty picture of what we need to know. Now, okay, so now moving on to a second example, same idea really. We're going to draw the sketch of the graph over the interval between 0 and 2 pi. So y equals sec of x plus pi on 3. It's really important to get your crossing points, okay? So, or your endpoints in this situation. Now, because we've got our domain, we can put our x value of 0 in there and an x value of 2 pi, which is what I've done here. And my calculator has told me basically my y value is going to be 2. Right, okay, cool. So we now know that. But what is a sec curve going to look like? Well, again, I tend to draw a really quick graph. Sec is cos. I'm going to do this. There's my standard cos. We've got pi on 2, pi, 3 pi on 2, and 2 pi. Now, in this situation, because it's sec of pi, x plus pi on 3, it means I'm going to move this to the left, pi on 3. So that now means that because I've got these points here, they are going to be asymptotes. They're not going to be at pi on 2 and 3 pi on 2. I'm going to take pi on 3 away from both of those values. Those are going to give me my asymptotes. Easy done. Once I've got my asymptotes, once I can draw those asymptotes on, wherever they're going to be here, for example, I know that my graph would normally look like this, and it would look like that, and it would look like this, okay? So again, that's nice and easy because I know that's still going to be at the point -1. I can work out what pi minus pi on 3 is going to be, so 2 pi on 3, okay? So I can work out the specific points at that point there. And now I can work out those endpoints there as well, because I know from my calculator that's going to be a 2, and that's going to be 2 pi minus pi on 3, whatever that's going to be, comma 2. And I can draw that sketch really nice and easily, okay? Yep, using some basic maths and the method stuff. And here is an example for cot of x minus pi on 4. Again, if you're, being sensible about this, you can use your CAS. Because, again, I've got the domain between 0 and 2 pi. Put 0 in there. I got -1. Put 2 pi in there. I get -1 again. And just to make my life that little bit easier, I'm going to solve for where that is equal to 0 between 0 and 2 pi. And again, what does that now show me? That's going to give me my crossing points. I can work out the asymptotes really easily because I know what the asymptotes would have been for my pi graph. For my tan graph. And I can work out where they would shift to. But my crossing points become really, really important. So again, if I was going to sketch this Making this important, we now know the red line is the one we're looking for. So we now, because we got that point there and that point there, we can mark them accurately. We know that that's -1 and we know that's -1. We can mark it accurately. The rest of it, and you've got your asymptotes, which you can work out. The rest of it should be relatively simple. All right, now, here are some examples, and I want to thank Cambridge so much for allowing me to use their examples. You guys rock. Thank you very much. If you haven't subscribed to my YouTube channel, it'd be great if you could. That'd be awesome. Right, in the triangle ABC, 90 degrees, x degrees, 6 and 5. Find AC. Are you kidding me? Is this a special exam or not? Because, as far as I'm concerned, I can use Pythag. So, for part A, we would know that AC squared is equal to 5 squared plus 6 squared. AC squared is 25 plus 36. AC squared is going to give me 61. So therefore AC is going to give me root 61. Did they give me units in this? Centimeters. So let's do my units. Okay. Find all the trigonometric ratios related to x degrees. Now again, the trigonometric ratio beforehand would have been sine, cosine, and tan. Right? So in this situation, they'd be effectively saying then sine of x would be opposite over hypotenuse, which would be 5 on root 61. The cosine of x is adjacent, which is 6 on root 61. And the tan of x would basically be 5 on 6. Okay, I know. And now, if we're going to do sine, we've got to do cosec of x. And we got cos, which would be sec of x. And we would do cot of x as well. And in which case, bearing in mind they are nothing more than the reciprocal of each other, we'd have root 61 on 5. We'd have root 61 on 6. And we would have 6 on 5. Complicated? No, not really. All right, now we get to useful properties. And much like we've had with all of the stuff we did in methods, both units 1 and 2 and 3, 4, we can come up with all of these symmetry properties. Am I going to show you where they came from? No. Under no circumstances would be here forever. But these are the type of things you put into your summary book. I don't know if they're on the formula sheet. I can't quite remember because VCAR this year changed again the formula sheet. But they are useful in the sense of the questions we're about to do now. So find the exact value of the following. Now, when we get to 11 pi on 4 or minus 23 pi on 4, 11 pi on 3, I start thinking in terms of, well, okay, can I turn that into a much better angle that falls between 0 and 2 pi? Because at the moment, that 11 pi on 4 doesn't fit between 0 and 2 pi. Now, if I look at the idea of 2 pi's, all right, because sec has got part of cos, and I'm looking in terms of 2 pi. Well, if I divide that by 4, that gives me 8 pi on 4. I'm looking at multiples of 8. All right, so 8 to 11 is 3 pi on 4. And hold on, 3 pi on 4. Okay, so what I'm now saying is I can write the sec of 11 pi, he says, 11 pi on 4 in a different way. That is the sec of 8 pi on 4 plus 3 pi on 4. Well, 8 pi on 4 is basically 2 pi, which means it's a revolution and that no longer exists. So they are exactly the same thing. Right, okay. So going back to my pen again. So can I work out the sec of 3 pi on 4? Well, that's the same as 1 on the cosine of 3 pi on 4. I draw a quick unit circle because I can. So that's all stations to Canberra. So 3 pi on 4 is basically going to be here. That's going to be giving me pi on 4. That's going to give me pi on 4. So cos in this is negative. So we are looking for cos, or the negative cos of pi on 4. So that's going to give me equal to 1 on the cos of negative pi on 4. Well, again, a quick triangle of 1, 1 root 2, and that's pi on 4. Or caught a herring minus 1 on root 2. So that's going to give me 1 on minus 1 on root 2, which basically gives me minus root 2. Now, again, I'm sure a lot of you are screaming at the screen going, wow, you overlabored that. I did. But just remember that not everybody doing special maths is finding it easy from day one. It takes time, it takes practice. And hopefully I'm sort of giving an idea of ways of doing this. And yes, you'll get faster and there are shortcuts to all of this. But hopefully, you know, I'm here to try and help all Right, the cosec of minus 23 pi on 4. Right, so I want to do 8. So 8 pi on 4 again is going to give me 2 pi's. 8, 16, 24. Ah, so if I can get to 24 pi on 4, 24 pi on 4. Ah, well, actually, so the cosec, he said, writing cos. So the cosec of minus 23 pi on 4 is the same as the cosec of minus 24 pi on 4 plus pi on 4. That's going to give me minus 20, but we now know that that is a multiple of 2 pi. So that's no good to me. So in which case I can now say, well, therefore, that's equal to the cosec of pi on 4. That's 1 on the sine of pi on 4. So again, a quick triangle of pi on 4, 1 root 2. There's pi on 4. Silly old Harry is 1 on root 2. So that is 1 on root 2, which is basically root 2. And there we go. Once again, now again, a lot of people out there will know the sine of pi on 4. And my advice is to rote learn these if you can. It makes life so much easier. But root 2 is my answer. What about this one? The cot of 11 pi on 3. Now, cot is tan. Tan repeats every pi. So we're looking at, so pi, we're looking at multiples of 3, 3, 6, 9. So I'm probably going to say 12, 3, 6, 9, 2 pi on 3. Don't know that one particularly well. Okay, so I can now write that the the cot, the cot of 11 pi on 3 is the same as the cot of 12 pi on 3 minus pi on 3. Right, well, 12 pi on 3 is basically a multiple of pi, so that's going to go. So I now know that is the same as, and I've written cos again, cot. So that's the same as the cot of negative pi on 3, which is 1 on the tan of minus pi on 3. Well, minus pi on 3, so pi on 3. So we've got 1, 2 root 3, and that's pi on 6. That's pi on 3. There we go. So tan trawling off America is root 3. So there we go. So we've got 1 on root 3, which is going to be minus root 3 because we're looking at the tan of all the places that are negative. So that's minus, which gives me, well, that's it, minus 1 on root 3. Sorry, my brain was working rather than teaching there, but ultimately using the same idea. Right, new identity, so much fun. Love it. Right, now we've already used sine squared plus cos squared. Try again. We've already used sine squared plus cos squared equals 1 in other areas of this course. In fact, we got it from the unit circle, if you remember. Now, using manipulation, we can actually get to 2 more important formulas. Now, for example, if I've got sine squared theta plus cos squared theta equals 1, and I divide both sides by sine squared theta. Well, sine squared divided by sine squared is 1. Cos squared divided by sine squared. Well, we know that tan is sine divided by cos. So sine squared divided by cos squared would be tan squared, but that's the other way around. Oh, well, it's 1 on tan squared. So that's going to be 1 plus 1 on tan squared is equal to 1 on sine squared. Well, hold on. We know that 1 on tan squared is cot squared. And we know that 1 on sine squared is cosec squared. And ka-ching, there we go. So I've just come up with this second formula here. That 1, oops, that's a horrible color to highlight. Why do I ever do that? 1 plus cot squared equals cosec squared. What? Let's highlight this for a moment. Let's lasso it and move it over here for a moment and see if we can do the same with the other one. So what have we got here? So let's start again with sine squared plus cos squared equals 1. Now I'm going to divide both sides by cos squared. So cos squared theta divided by cos squared theta divided by cos squared theta. Right, sine squared divided by cos squared, we've just decided is tan squared. That's going to give me 1. And 1 over cos is sec. And have we got tan squared? Hold on a minute, my formula looks different. Well, that's just because they've rearranged it. So basically we get sec squared minus tan squared is equal to 1. Sec squared minus tan squared equals to 1. That'll work. Doesn't really matter which way around. But so now, here we have 2 more useful formulas to add to our entourage. Now, why would we work out our entourage? Well, there's lots of different things we can do with these particular questions. And one of the ones we used to do in the United Kingdom, which I absolutely adored, was trig identities and simplification. Right now, again, it's a bit of a trick, and there's no hard and fast rule that I can ever work out with these ones, but it says, for example, we can write this as sine cubed x. It's exactly the same as the sine cubed of x. And you're going to say, how? And I'm going to say, well, the first thing is we're going to take out cos x as a factor, which gives me 1 minus cos squared x divided by cot x. Right, now we'll come back to that one in just a moment, because I know from, having this drummed into me that 1 minus cos squared is sine squared. So that becomes equal to the cosine of x times by the sine squared of x. Now I'm going to write that as 1 on, I keep doing cos, I'm sorry, cot x. Well, cot x is cos over sine, so 1 over cot x would be tan x. Exactly. So that's going to give me the cosine of x times the sine of squared of x times the sine of x over the cosine of x. Your cosine of x cancels, and then you get sine squared times sine. Gives me sine cubed of x. This is why I love this. It was a little bit like Sudoku, really. Love a bit. Right, now let's use some practical applications. If tan x is equals to 2, and x is in 0 to pi on 2, right? So again, we're now only interested in x values falling within 0 and pi on 2, inclusive. Find sec x. Right, well, okay, well, how on earth are we going to find sec x? Well, we know that sec squared x is equal to 1 plus tan squared x. And you're going to say, how do we know that? Come on, we just did it. All right, so I'm going to move that up there. Right, so sec squared x equals 1 plus tan squared x. Well, I know what tan x is, so that's going to give me, why won't my pen work? 1 plus, well, tan of x is 2. That's going to become 2 squared, which is 1 plus 4, which gives me 5. Yay! But that's sec squared of x, all right? So therefore, the sec of x is going to be plus or minus the square root of 5. Okay, now we only want sec x to fall in 0 and pi on 2. Now, what on earth does my graph of sec x look like? Well, that's cos. Okay, and we want it between 0 and pi on 2. Well, that's pi on 2 there. Yep, but we've got to realize that for sec, that was an asymptote. So we're going to have values here. So we are basically looking for the positive value there. And so just through process of sort of, I'd say, mathematical manipulation, we know, therefore, for that domain, sec x would have to be root 5. Okay, cool, that's the first one. What about the cosine of x? How on earth am I going to find the cosine of x? Sounds a little bit complicated. Not really, because if you remember, we know that sec x is 1 on cos x. So cos x must be 1 on sec x. And we know what sec x is, we've just worked it out. So it's going to be 1 on root 5, and rationalizing, we're going to get root 5 on 5, and there is my sec x. What? So again, to be honest with you guys, this is really just a trick. I'm going to highlight that and make it a little bit smaller. Resize, make it a bit smaller. Move that up there for the moment. Let's move this up here. Right. So now let's see what we've got. Sine x. Well, we know that tan x is equal to sine x over cos x. What are we trying to find? Sine x. Well, therefore, sine x is cos x times tan x. Now, how's that going to help us? Well, we've just worked out what cos x is. It's root 5 on 5, and we know that tan x is 2, so it's 2 root 5 on 5. See, again, to me, this is all just tricks and tricks and tricks and tricks. What about cosec of x? We know that cosec of x is 1 on sine of x. We've just worked out what sine of x is. So cosec of x is the reciprocal of that, which is 5 on 2 root 5. And again, we could rationalize that. So that's going to give me, what's that going to give me? 5 root 5 on 2 times 5, which is 10, which is going to give me root 5 on 2. Sorry about the lack of space there, but yeah, I ran out of space. And obviously we can use our CAS calculator for this, because the trick to the multiple choice questions in the VCAR exam is to make sure you know how to use your CAS really, really well. I know there's a lot of UDFs out there, which at some point I'm going to explore and maybe do a video on that. But for now, let's just look at the idea here of, first thing I'm going to do is I'm going to fire up my calculator and I'm just going to solve for my initial solution. All right, now x equals pi on 2 minus 10 to the minus 1/2. Doesn't look particularly helpful, but because my calculator is in exact mode. Now, a lot of people go, why on earth did you do the next step? Well, believe it or not, to be able to then define a value of that makes life a lot easier. Yeah, because although it looks like here we have x equals, and you should theoretically be able to use x, it doesn't work that way. So what I've actually done is just defined a function or a value a and said, well, okay, let that be the solution. And the calculator's gone, all right, I remember that. So now to find things like sec of x, which is effectively 1 on the cos of a, I just do 1 of cos of a, and it's root 5. Now, again, the great thing here is because I have limited my domain as part of the question, then the calculator is going to give me the right values for each of these. And so, as you can see, I've got root 5, 2 root 5 on 5, root 5 on 5, and root 5 on 2, which are all the values I got before. So defining that value as a specific constant makes life much, much easier. And again, remember, that is a dot, dot, and equal sign to make it assigned to. All right, now bearing in mind that was a long video, hopefully it was useful. Have we understood what the cosec, sec, and cotangent functions look like? Yep. Have we looked at useful properties? Yep. And have we understood how to use the CAS? We have. If you can subscribe to my YouTube channel, that would be amazing. Greatly appreciated if you could. Go over to mathsguru.com. This course is going to be populated over the next few months. Hopefully it's going to be useful. I look forward to seeing you in another video, but I'm going to call it a day for now. Take care. Bye-bye.